Let's talk about the alternating series remainder theorem, also called the alternating series estimation theorem. So what this theorem pertains to, you can see here in the scenario I've pre-written. So you have an alternating series, and it's written with like a -1 to the whatever here, just to show that it's like the perfectly alternating plus then minus, plus then minus. So it's one of those perfectly alternating series. And you would only use this theorem if that series is convergent using the alternating series theorem. So it's something that's definitely already convergent. And then we know that if you have a convergent series, you would want to estimate the value of the entire series, the full sum, using some sort of partial sum. So Sn approximates the full sum S. So in that case, the alternating series remainder theorem gives us this statement right here that we can use to estimate the error. So we have Rn, which is the difference between what we're trying to approximate and our partial sum. That remainder error is always less than or equal to the magnitude of the first term that is not included in that partial sum. So Bn plus 1 is the next term, right? So if this is the 10th partial sum, this is the 11th term. And then it's without the -1 part. So it's just the magnitude or absolute value of it. We're not going to worry about negative numbers in that spot because that also wouldn't make sense in this context. Okay, so let's see this in action. I have two examples ready for this video. The first one here, we're just going to kind of explore what this statement actually looks like in a specific context, and then we'll answer a different kind of question in the second one. So here I have the sum from k equals 1 to infinity, -1 to the k, 1 over k. This is also called the alternating harmonic series. If we plug in k equals 1, we have -1 to the 1, 1 over 1. And then we plug in k equals 2, k equals 3, and so on. And if we simplify these terms just a little bit, we can get a really good glimpse at what this series really looks like. So we have -1 plus 1/2 minus a third, and then it would continue plus a fourth minus a fifth, and so on forever. That's your alternating harmonic. So we're not going to do it in this video because we have other things to worry about, but do note that this series is a perfect fit for the alternating series test. Which would show very quickly that this is convergent. So we've passed kind of the condition here. It's alternating and it's convergent by the AST. So now we have that the error of the nth partial sum in approximating the full sum is less than or equal to the magnitude of the first excluded term. Okay, so let's say, for example, we want to estimate the entire sum, which above is what we're calling S, using S3. Okay, so what that would mean is S3 here is the sum of the first three terms, so -1 plus a half minus a third. If we make a common denominator here, that should come out to -5 over 6. And then what this theorem tells me is that this is no more than 1/4 away from the correct answer. Or oops, that should not be a 4. We just did S3, so we're talking R3. Whoopsie. So R3, the error of this approximation and approximating that, is less than or equal to B4. So we have an N here, an N plus 1 here. And B4 is this guy right here, right? So I used the first three terms. So the error upper bound is the magnitude of the first excluded term. So this is no more than 1 over 4 away from the exact correct answer. And if I was going to, let's say, add up the first 4 terms for a closer estimate, then I would be worried about R4. So that error is no more than B5, which is still positive 1/5, right? So we're always taking the magnitude of the first excluded term from the partial sum. So for this one, it would just be a fifth, even though the whole term is -1/5. Okay, so let's move on to our second example. We weren't really answering particularly a question here, just kind of exploring what the formula gives us. Here, we're going to answer a question. So we're given a slightly different alternating series. We have -1 to the k, 1 over k squared plus 1. This is also convergent by the AST. We're not going to go into details here, but it does pass the conditions that we need. So this problem is asking us to estimate this sum with error less than, let's say, 1/8 for this problem. Okay, so what we need to do, instead of, like in this last example, kind of choosing a partial sum and letting the excluded term be the error bound, we're going to fish for the error bound we need and backtrack it to the appropriate sum. All right, so I'm going to write out the first few terms of this series. So k equals 0 to infinity, -1 to the k, 1 over k squared plus 1. If we plug in k equals 0, we just get a plain 1. If we plug in k equals 1, we get -1/2, and then plus 1/5 minus 1/10, and that should be sufficient for our needs here. Okay, so I'm going to fish for the first term that meets this condition. So the first term that is strictly less than 1/8. So here, that is this guy right there. So the fourth term of the series, 1/10, or technically -1/10, is the first one whose magnitude is less than this desired error 1/8. So it's the first term whose absolute value is less than 1/8, which means that I want this to be the error bound number right here. So I'm going to go back and have that 1/10 be the first excluded term from the partial sum. So I'm going to use S3 here, the sum of the first 3 terms, to estimate the series. So then R3 is less than or equal to B4, which is 1/10, which as desired is less than 1/8. Okay, so our actual answer is the sum R3. That's 1 -1/2 plus 1/5. And if we make a common denominator, we should get 7 out of 10. So this is an estimate of the full value of the series. And I know from this formula that the error in this estimate is strictly less than 1/8 as desired. So the only other time that this approach would change slightly is if this error requirement were not in the first handful of terms here, right? So in most problems, especially without a calculator, if they say estimate the sum of this alternating series with error less than whatever number, you do exactly what we did here. You write out the first handful of terms, you find the first term that meets that requirement, and let that be the first one left out of the partial sum. So you add up everything up until it. Now, the only time this wouldn't work is if it was going to be, like the 15th, the 100th term of the series that met that condition. Then, we would really kind of run out of patience before we found the term that did it. So the alternative, if you find that it's not in the first handful of terms and you're like, oh, wow, I'm really going to have to go way out to find this, is you could solve algebraically for which term has that property. So in this one, it would be overkill, but we can still show the work. So we'll call this an or on the side here. Instead of fishing for that fourth term, we could say, well, when is 1 over k squared plus 1 strictly less than 1/8? And I could solve algebraically for the k value that does it, and that kind of immediately brings me to the correct part of the series.